In simulation, swarm robotics operate in a mathematically perfect void, but in physical deployment, those identical algorithms yield erratic drift, broken formations, and systemic failure. That failure stems from a dependency on centralized infrastructure. Most testing environments require external anchors, like global positioning systems, ground control stations, or off-board motion capture cameras. When you remove those external anchors, standard swarms immediately fracture. Real-world latency, sensor drift, and strict geofence limitations degrade the central network, causing individual drones to lose their spatial awareness. To deploy a swarm in the physical world, the architecture requires abandoning centralized control entirely. Every calculation must happen on the node itself. Until a swarm can independently track its own units, route its own data without a central hub, and autonomously comply with physical airspace constraints, it remains a simulated theory rather than a deployable tool. Solving this deployment bottleneck requires a strict three-tier architectural framework. The first tier is hardware. Individual nodes need the onboard processing power to execute local tracking and sensor fusion, entirely independent of outside infrastructure. The second tier is the network. The fleet must maintain a self-healing, ad hoc web that dynamically routes payloads between drones as they move and reposition. The third tier is the environment. The pathing algorithms must integrate strict, emerging aerospace laws directly into the swarm's control logic. Swarm engineering requires integrating localized hardware, decentralized networking, and regulatory control laws. To see how the hardware tier operates, we look at the S-drone, an open-source platform engineered specifically for strictly onboard processing. This exploded view shows the S-drone's flight control electronics, anchoring autonomy on a Pixhawk 4 flight controller and downward-facing cameras. This circuit board diagram details the interface managing power distribution and high-speed data transfer between the computer and flight controller. Notice the deliberate absence of off-board sensing modules. The drone is physically isolated from ground stations by design. This strict isolation imposes heavy operational limits. The onboard hardware caps the maximum flight time to around 15 minutes and limits the processing payload capacity available for vision-based navigation. This exact hardware stack creates a difficult kinematic problem: how to accurately track moving peers at high speed without access to a global coordinate system. Lacking an external reference, they rely exclusively on environmental markers and local sensor fusion to understand their position relative to the fleet. This schematic illustrates cooperative sensor fusion. Here, two S-drones share an environmental anchor, an April tag. Drone A calculates the mathematical roto-translation from its optical frame to its physical body frame, using the ground tag as origin. Next, Drone A broadcasts its own ID, alongside the ID of the tag it just detected, across the local network. Drone B receives the broadcast and checks its downward-facing camera to see if it has a matching tag ID in its field of view. Once Drone B confirms the match, it unicasts its feature-level pose data back to Drone A. The result is precise relative positioning. Both UAVs calculate the 2D position and orientation of the other drone with respect to their own body frames. When scaled up, this continuous tag-based handshake allows dozens of drones to maintain complex follow-the-leader formations without ever checking in with a central command node. By utilizing the physical environment as a shared mathematical anchor, the swarm achieves inter-robot tracking while remaining completely decoupled from global positioning systems. Expanding this local tracking to a full swarm of 10 or more drones mapping a natural disaster introduces the second tier, the network. In a centralized system, a dropped ground link or a damaged command node halts the entire fleet. To prevent this, the swarm relies on dynamic routing. Drones autonomously ping nearby teammates to construct continuous, ad hoc data pathways on the fly. If a drone enters an error state, it drops out. The network instantly heals around the gap, and a replacement drone is added to the fleet without disrupting the ongoing global task. This resilient network is necessary to handle a heavy operational payload, mapping terrain in real time following a natural disaster. Traditional camera photogrammetry is highly inaccurate in these scenarios, as dense vegetation and low light conditions obscure the ground. This animated diagram shows the solution, integrating LiDAR sensors to fuse overlapping point clouds into a single 3D topographic mesh. Instead of pushing data to a server, this fused terrain map is processed locally, distributed across the decentralized nodes. Running an onboard region-based convolutional neural network, the swarm can identify specific disaster-struck geographic areas with 92% accuracy in real time. This combination of dynamic routing and decentralized data fusion allows the swarm to execute heavy compute tasks that would instantly overwhelm a traditional centralized network. But hardware and network capabilities are bounded by the third tier. Airspace law imposes specific constraints on autonomous swarm operations. In May 2026, the FAA published a Notice of Proposed Rulemaking regarding Section 2209. This introduces Unmanned Aircraft Flight Restrictions, or UAFRs, giving 16 critical infrastructure sectors the authority to establish designated drone-free zones. This spatial diagram illustrates the strict dimensions of a standard UAFR. The restricted volume is bounded precisely by the facility's property lines and capped at 400 feet above ground level. These zones are not absolute bans, but entering legally requires strict compliance. The swarm must continuously broadcast remote ID, provide advance notice to facility managers, and guarantee transit through the airspace in the shortest practical time. Hardware and network autonomy are useless in commercial deployment if the swarm's control laws cannot proactively parse and navigate dynamically restricted legal volumes. Physical deployment means forcing all three tiers to operate simultaneously. A swarm must map a disaster zone, maintain its network, and route legally around a critical infrastructure site in real time. The physical nodes must execute strictly onboard processing, maintaining their spatial awareness without ground stations. The operational payload relies entirely on the resilience of dynamic routing and decentralized data fusion, and the control algorithms must be hard-coded to respect UAFR boundaries and remote ID mandates. Systems engineers refer to this as the swarm paradox, the technical push for totally decentralized drone technology operating squarely within increasingly centralized airspace control. Resolving that paradox requires testing grounds. Current state-of-the-art open-source platforms provide the exact environment needed to integrate these three complex layers. Autonomy is defined by the swarm's ability to successfully navigate the physical, digital, and legal constraints of the real world.